following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Modeling decision under uncertainty turns out to be a critical part of what we do in economics, and I'll spend today's lecture talking about it, about this set of issues. And let me just say, the uncertainty you face now is nothing compared to the uncertainty that you'll face later in life. So you have uncertainty now about whether you should study for the final or carry an umbrella or go on a date with this person. I've got uncertainty about whether I should refinance my mortgage or which college to send my kid to or how much life insurance I should buy. Uncertainty only gets more and more important as you move on in life. This is an important issue. Now, how do we think about uncertainty? Well, the tool that we use to think about uncertainty is, once again, to make simplifying assumptions which allow us to write down sensible models but which capture the key elements of what we're thinking about. And the simplifying assumption here is we move to the tools of what we call expected utility theory. Expected utility theory. Okay? And so basically, the way to think about expected utility theory is the following. Imagine that I offered you guys in this class a choice. Okay? And I'm going to say right now, there's no right answer to this. Okay? But I do want you guys to answer me. There's no right answer. Here's the question. I'm going to give you a choice. I'm going to flip a coin. I have a coin in my pocket. I'm going to flip it. And I'm going to offer you guys the ability to make a bet. If it comes up heads, you win $125. If it comes up tails, you lose $100. Heads, you win $125. Tails, you lose $100. Okay, no right answer. How many people would take that bet? How many people would not take that bet? Okay, so that's very good. That's the typical set of responses I get to this. Now, what's interesting is to think about the parameters of that bet. And to think about it, let's take a step back to something we've discussed already this semester, the concept of expected value. What's the expected value of that gamble? Expected value, if you remember, is the probability of each outcome times the value of that outcome. Okay, the probability of each outcome times the value of that outcome. That is, remember expected value, which you defined before, it's the probability that you lose times the value if you lose, plus the probability that you win times the value if you win. Okay, it's the expected value of a gamble. So in this context, the expected value is there's a 50% probability that you lose, so 0.5, and if you lose minus $100, plus a 50% value that you win. It's flipping a coin after all. And if you win, you won $125. So the expected value of this gamble is $12.50. On average, if I did this enough times, you would win $12.50 per time. Okay, statistically, if I did this enough times, you'd win $12.50 per time. So in other words, we say that this is more than a fair bet. A fair bet is one with an expected value of 0. A fair bet has an expected value of 0. Okay, so fair bet would be tails you win 100, tails you lose 100, heads you win 100. This is a more than fair bet. Okay, a more than fair bet. There's more than 0 expected value. Yet, the majority of you would not be willing to take this bet. Okay, in fact, the majority of people would not take this bet. Why is that? Why is it that I've dictated a bet which has a positive expected value and yet people won't take it? Yeah?
But wouldn't that also depend on how much money you have? So
It will absolutely depend on how much money you have.
right, so if I were a richer person, then losing $100 isn't as important to me as like a chance of getting $125.
Okay, so flesh that out. Why is that? Why is that basically it would matter how much wealth you have? Because no matter how much wealth you have, this math is unimpeachable. It's always a good bet. So why is it that at your state without much wealth, your state is college students without much wealth, what is it about you that caused you not want to take this bet that's more than fair?
So basically, for me, the risk of losing, or the state I will be in after I lose is much greater, will hurt me a lot more than what I will be in if I earned that.
Exactly. And there's two possible reasons for that. One, we're going to push off to the very end of the lecture. But the main reason we're going to focus on is because individuals do not consider expected value, they consider expected utility, and individuals are risk averse. Individuals' expected utility is going to differ from expected value when individuals are risk averse. Expected utility is not going to be the probability times the value if you lose. It's going to be expected utility. It's going to be the probability that you lose times the utility if you lose, plus the probability that you win times the utility if you win. And utility is not the same as value. Importantly, because utility functions exhibit diminishing margin utility. Utility functions are not linear. Utility functions are nonlinear, and in particular, there's diminishing margin utility. And with diminishing margin utility, okay, you're going to not want bets where there's a chance you lose is equal or even maybe is equal or even a bit smaller than the value that you win. Okay? And the basic point is that the joy of winning is smaller than the pain of losing with diminishing margin utility. Yeah?
Isn't there also a statistical side to this that because we don't know how many times we're doing a bet, it might just be once, we're a lot more comfortable if we can, let's say, use the law of large numbers and say, okay, it's going to eventually even out to us when you 12, 15 game. But for the first, let's say, 10 or so games, we might get really unlucky and flip 8 tails in only 2 minutes.
But once again, if you weren't risk averse, you wouldn't care about that. Hold that thought. I'm going to explain why that isn't true. Okay, so just hold that thought. Okay, so now let's imagine that your utility function is of the typical form we've worked with before, the typical diminishing margin utility form we've worked with before, where utility is the square root of consumption. Okay, you're casting your mind back to consumer theory here. Okay, you're going to have to start integrating the course now, both consumer and producer theory. So remember, it's the typical diminishing margin utility function we worked with was u equals the square root of c. Okay? Now, let's say you start with consumption of 100. Okay, imagine you consume your income. Let's say you have consumption of 100. Well, then your utility is 10. Okay, if you start with consumption of 100, your utility is 10. Okay? Now let's calculate the expected utility of this gamble. Well, the expected utility of this gamble is that there's a 50% chance that you win, that you lose. And if you lose, what's your utility? Well, you lose 100, so consumption goes to 0, so utility is 0. Okay? Plus a 50% chance that you win. Well, what if you win? Well, if you win, you go from 100 to 225. So utility is the square root of 225 or 15. Okay? So your utility is the square root of 225 or 15. So it's half chance of having 15. So, I'm sorry, so this is a negative. Yeah, I'm sorry. So utility, if you take this gamble, is you end up with a utility of 7.5. So utility falls. You move from a utility of 10 without the gamble to utility of 7.5 with the gamble. Utility is lower with the gamble, which is why people decided they didn't want to take that gamble. Utility is lower. Okay? And the reason is because given a utility function of this form, you are sadder about losing than happier about winning. Okay? And to see that, we can see that graphically in figure 20-1. Okay? This graphs utility against wealth. We don't really usually graph utility because it's not cardinal, remember, it's just ordinal, but this sort of gives you a sense of the intuition. This is a graph of utility against wealth levels. So you start at point A. You start with $100 in wealth, or which is consumption, and utility of 10. Now, I give you a choice of a gamble. That gamble has a 50% chance of leaving you at 0 and a 50% chance of leaving you at point B. So your utility, an expected value, is the midpoint of that chord that runs from 0 to B, or point C. Your expected utility is lower than your initial utility. Why? Because utility is concave. You are made so sad by getting to 0 that it vastly overcompensates the happiness you feel moving to 225 because of diminishing margin utility. Okay? Because basically, think of it this way. Imagine this was your actual income. Let's take the point about the size of the gamble relative to income seriously. Imagine literally I was asking you to gamble your entire income for the year. And if you lose, you starve to death. And if you win, you get to eat extra nice. Well, clearly, the disutility of starving to death vastly outweighs the extra utility of eating well. Okay? So you can, in that extreme example, if this was your entire wealth, you can see why you would have a situation where you wouldn't want to take that gamble. Because if you lost, you die. Okay? And basically, risk aversion arises because basically, with diminishing margin utility, you're made so much sadder, that steepness at the bottom, you get so much sadder as you get towards zero, that it vastly overcompensates the flatter part as you move above with your initial point. Okay? So as you can see, you're going to end up not wanting gambles even if they're fair. Gambles that are fair, that is positive expected value, might still lead negative, might still lead to a reduction in your expected utility. Okay? Indeed, let me go further. You dislike this gamble so much that if I said the following, I, as your teacher, I'm going to force you to take this gamble. Imagine we didn't have it's like 100 years ago where teachers could beat students and stuff. Okay, I'm going to force you to take this gamble unless you pay me. You would actually be willing to pay me to avoid taking this gamble. How much would you pay me? Imagine utilities in dollar terms. Okay, imagine we're actually measuring utility in dollar terms. How much would you pay me to avoid taking this gamble? If I said you either take the gamble or you pay me, you're starting with utility of 100. Yeah. Well, so you would, the difference between the two utilities. So utility is 100 here. Here utility is 7.5 squared, so 56.25. So you would actually pay me $43.75 to avoid taking this gamble. Think about that. I've offered you a more than fair bet, a very good bet, which on average will yield you a positive $12.50. Yet you will pay me $43.75. You will pay almost half your entire wealth to avoid taking that gamble. That's pretty incredible if you think about it. That I've offered you a more than fair bet, and yet you will pay me more than half your wealth, almost half your wealth, to avoid taking that bet. Okay? So another way to see this, let's look at this another way. How large would I have to make the positive payoff for you to take the bet? Think of it that way. How large, right now I said you win 125 with heads. How much would you have to win with heads if you want to take that bet? Yeah. Then tell us how you figured that out.
Because you need to have at least the same utility as you had before from the expected utility. So the only way for that to happen is for your utility to be 20 if you win.
Exactly.
So that's 20 squared is 400. You start with 100, something like that.
Right. You need to win 300 because I need to take your utility to 20 if you win. Only then would you be willing to take this gamble. So another way to say it is that's how fair a gamble would need to be, how more than fair it needs to be before you take it. You'd need me to pay off 3 to 1 on a 50% chance for you before you take the bet. And this is just with a typical looking utility function of the kind we worked with earlier this semester. You didn't look at this semester and say, wow, that's a bizarre utility function. We got sensible answers on our problems and problem sets and tests and things, examples from square root of c. That seemed like a sensible function. And yet it yields these incredibly wild predictions, okay, that you would pay people almost half your wealth to avoid engaging in a more than fair bet, okay, and that you would need the odds to be like 3 to 1 before you even consider taking a bet. That's the power of uncertainty and the power of risk aversion. Really, risk aversion, it's just the power of diminishing margin utility. Okay? It's the power of diminishing margin utility is so key to driving our decisions. It's the fact that that first pizza means so much more to you than the 5th pizza. That you really hate outcomes that don't let you get the first pizza. And as a result, you need to be paid, you will pay a lot to be forced into a situation where you don't get any pizzas. Okay? You'll need to be paid a lot in the state where you do win to deal with the state where you don't. Okay? Questions about that? Now we could change this example some interesting ways to understand it. So let's change the example to say instead, let's talk about some alternatives to this example and how they affect our intuition. First alternative, imagine your utility function, instead of being square root of c, your utility function was 0.1 times c. A linear utility function, not a nonlinear utility function. Okay? In that case, we can now say that in that case, you actually would take the gamble. Because utility, there's a 0.5% chance of 0 plus a 0.5% chance, and I chose 0.1 times c because your initial utility is still 10 then. Okay, I normalized this, so starting with your bundle of 100, you still start at 10. Okay, so it gives the same starting point as a square root function. Okay, but now your expected utility from this gamble is 0.5 times 0 plus 0.5 times if you win 125, your utility is 12.5. Okay? I'm sorry, it's 222.5, my bad. 22.5. So your expected utility is 11.25, which is higher than your starting utility. So you would take this gamble. What's changed? No diminishing margin utility, because now we are no longer risk averse. We are what we call risk neutral. A linear utility function yields risk neutrality. And once you're risk neutral, you only care about expected value. Risk neutral consumers would only care about expected value. Okay? And so a linear utility function leads to risk neutrality. Since you don't have diminishing margin utility, then you take any bet that's fair. You don't care. You're indifferent in winning a dollar and losing a dollar with this utility function, right? Doesn't matter if you go up or down. The joy you get from winning is the same as the pain you get from losing. Whereas with this utility function, the pain you get from losing exceeds the joy from winning. Okay? We can see that graphically in the next figure. Figure 22, the case of risk neutrality. Here you start at point A. Okay? You have 100 and your consumption's $10. Your utility's 10. Okay? Now I've offered you a gamble with a 50% chance of getting 0 and a 50% chance of getting B. Well, that yields an outcome of C, which is a higher utility. So since utility is linear, you're risk neutral, and you'll take any fair bet. Okay? We can go further. What if your utility instead was of the form U equals C squared over 1,000? What if this was your utility function? Once again, your initial utility, U of 100, is 10. Same starting point. Okay? But this is a utility function, which now, if you do this gamble, your expected utility is 50% times 0 plus 50% times 225 squared over 1,000. Okay? Which is 25.3. A huge increase in utility from this gamble. So your expected utility with the gamble is 25.3. A huge increase in utility. And that's because this is an individual where the shape of the utility function has changed, where they don't have diminishing margin utility, they have increasing margin utility. We've never worked with utility functions like this before. These are individuals we call risk-loving. That is, they are made happier by another dollar, by winning a dollar, than they made sadder by losing a dollar. It's the opposite of all the intuition we developed earlier in this course. It's a crazy utility function. But the notion of a risk-loving utility function is one where literally a dollar that moves you up makes you happier than a dollar that moves you down makes you sadder. You can see that in figure 23. Okay? Figure 20-3. Here's a risk-loving utility function. The individual starts at point A. They now have a choice of a gamble that leads, they have a choice of a gamble where they can have a 50% chance of landing at 0 and a 50% chance, Jessica, that B should be down at the intersection of dashed lines. A 50% chance of landing at B at the intersection of the dashed lines. You take the average of those two and it's C. Their utility is way higher with the gamble than it was without the gamble. In fact, we could go further. With a risk-loving person, they would actually take an unfair bet. Consider the following bet. Tails, you lose 100. Heads, you win 75. That's a bet with a negative expected value. A negative expected value. Okay? Neither the risk-averse nor the risk-neutral person would take that bet, but a risk-loving person would. If you work out the math, that bet gives them a gain in expected utility. That is a bet with a negative expected value, gives them a gain in expected utility. Why is that? Because it's the opposite of diminishing marginal utility intuition. They're made so much happier by winning. So much happier by winning that they're willing to take a bet even if it's a negative expected value. Just like the risk-averse person is made so much sadder by losing, they won't take a bet even if it's more than fair. So you can actually develop all the opposite predictions from a risk-loving person. They'll even take unfair gambles. Now, by the way, I skipped over your earlier question of risk neutrality. With risk neutrality, you see it doesn't matter if you do it 100 times or 1 time. Okay? If you're risk neutral, you should take the bet anytime because the expected value is still positive. Now, you're thinking about risk aversion, where in some sense your risk aversion is about you're more confident as the numbers go up. But if you're risk neutral, take it about how many times I offer you that bet. Okay? So to extend this further, let's go to a third extension. Now imagine, which will develop this intuition further, now imagine that I offer you guys a different gamble. And once again, I really want you to answer honestly. Don't try to game me. Answer honestly. Now the gamble is heads. If I flip a coin, heads, tails, you lose $1. Heads, you win $1.25. Okay. Now how many would take that gamble? How many would not take that gamble? Okay. I hope you're answering honestly, but maybe you're just thinking ahead and realizing that that gamble is very different. And why are people more willing to take that gamble, even though than they were willing to take the previous gamble? Same risk-averse people. Yeah.
The difference in utility is almost negligible, right?
Exactly. In particular, the utility function is locally linear. That curved utility function, as you get closer and closer to that initial, let's go back to figure 20-1. As you get closer and closer to A, you could draw essentially a linear segment. So for an infinitesimal bet, utility is linear, right? So it's linear at point A. So for small bets, you become risk neutral. Even a risk-averse person moves towards risk neutrality as the bet is small relative to their resources. This was the point that you were making, that basically if you're a rich person, you'd probably be happy to take the $100, $125 thing. I'd be happy to do that. I'm a rich guy. Okay? I'd be happy to do that. So basically, what determines your level of your willingness to take a bet is going to be about what's at stake relative to your resources. Okay? What's at stake relative to your resources. And what you can see is that if you solve the math here, that basically expected utility, even with square root of C, is positive for that smaller gamble. Okay? Because as it gets small relative to the $100 you start with, you become roughly risk neutral, and then you go ahead and take the gamble. Okay? So at the end of the day, what's going to determine whether you're going to take a gamble is going to be your level of risk aversion and the size of the risk you're taking relative to your resources. The more risk averse you are, and the bigger the gamble, the less likely you are to take it at a given level of fairness. Okay? Questions about that? All right. So now that we all understand expected utility theory, now we're going to go on and talk about why this matters in the real world and how we use it. And I want to talk in particular about 2 applications, insurance and the lottery. Okay? Let's start by talking about insurance and why people have insurance. Because, in fact, given what we learned to this lecture, there'd be no reason for insurance. This lecture tells us why people have insurance, which is that basically, because there's diminishing margin utility, you're made so much sadder with a negative outcome, you're willing to pay to avoid it. Remember we talked about that you'd be willing to pay almost $44 to avoid forcing to take that bet? That's what insurance does. Insurance allows you to avoid taking gambles. That's what you think of insurance is. It's a way to avoid taking a gamble. You're gambling, you're going to get sick. You're gambling, your house is going to burn down. Okay? These are gambles you face that are forced on you by nature. What insurance does is allow you to avoid taking those gambles. And just like you'd pay me to avoid the $100, $125 gamble, you're paying Aetna to avoid gambling that you might have to go to the hospital. Okay? So let's say there's a 25-year-old who's deciding whether to buy health insurance. And let's say they're a 25-year-old guy, totally healthy. I say guy because there's no risk they're going to have a kid. So basically, totally healthy, basically zero chance they're going to use the doctor except if they get hit by a car. Okay? So imagine the situation is that you've got a 25-year-old with an income of $40,000, an income of $40,000, okay? And let's say that there's a 1% chance they'll get hit by a car. It is Cambridge after all. So every time you cross the street, there's a 100 chance you get hit by a car, okay? So there's a 1% chance that you get hit by a car. If you get hit by a car, you're going to suffer $30,000 in hospital bills, okay? So what that means is, and let's say your utility function is square root of C. So you're a risk-averse guy. Okay? So let's say that I then come to you and say, look, each year there's an expected value, there's an expected cost to you of getting hit by a car of $300. How do I calculate that? Well, every year there's a 1% chance you get hit. They're independent draws, say. You know, if you get hit this year, it doesn't mean like suddenly you're safer. Okay, so it's random. It's just crazy drivers. So there's a 1% chance you're going to get hit every year. And if you get hit, there's a $30,000 cost. So every year is the expected cost to you. The opposite of expected value is expected cost of $300. So let's say I offered to sell you insurance for $300. I offered to sell you insurance in a way where, on average, if you lived, if you lived an infinite number of years, you would pay out in premiums what you'd get in benefits. Right? If you paid $300 a year and lived forever, or lived for many, many years, large numbers, enough years, okay, then basically you would pay out in premiums what you'd collect in benefits. You'd get hit once every 100 years, and every 100 years you'd have paid $30,000 in premiums, and you collect $30,000 in benefits. So that's what we call actuarially fair insurance. Actuarially fair insurance is insurance where you pay the price of the insurance equals the probability of the bad outcome times the cost of the bad outcome. That's actually fair insurance, where the price you pay is the probability of the bad outcome times the cost of the bad outcome. That's fair because over a large enough population, the premiums that get paid in will get paid out in the form of claims. Okay? Now, let's ask, what is your utility if you do not or do buy insurance? So the first thing you say, I'm 25-year-old, screw it, I'm never going to get hit by a car, I'm not going to buy insurance. What's your utility with no insurance? No insurance. Well, if you have no insurance, there's a 1% chance, 0.01, that you'll lose $30,000. You'll get hit by a car and lose $30,000. Your income's $40,000. So there's a 1% chance that you'll end up with a utility which is square root of 10,000. Okay? And there's a 99% chance. There's a 99% chance you'll end up with a utility that's square root of 40,000. Okay? You work this out, and the answer is you get 199. So utility without insurance is without insurance is 199, which is pretty close to utility, just if you weren't hit by the car, because it's so rare you get hit by the car. So utility is 199 without insurance. Now, let's ask the question, how much would you be willing to pay to have insurance? How would we figure that out? $300 is the actually fair premium. Okay, but now it's a different question. I'm an insurance company, I want to make money. Okay, I don't want to just charge you actually fair premium. The insurance company makes no money with this premium of $300. Say the insurance company wants to make money. How would we figure out how much would you be willing to pay, this 25-year-old, be willing to pay to get insurance? How would we figure that out? Yeah.
Maybe you could keep the utility function constant.
Keep the utility value constant. Exactly. You'd have to ask, well, how much would I be willing to pay to have insurance which would protect me and leave me at the same utility level? Obviously, I have to be a little bit higher, but let's just set it equal. So in other words, if I bought insurance, my utility with insurance, there's a 1% chance that I will get hit by the car. In that case, what happens to me? Well, if I get hit by the car, I get $10,000. I make 40. I lose 30. Let me actually write it out. If I get hit by the car, what happens to me? Well, I make 40,000. I always make 40,000 each year. I lose 10,000 because I get hit by the car. I lose 30,000. I'm sorry, because I get hit by the car. But then the insurance company pays me 30,000. They pay off my debts. So then I gain 30,000. Okay, so these things cancel. But I have to pay the insurance company premium. So I have to pay some amount X. Okay? If I don't get hit by the car, I get my 40,000 income, but I still have to pay the insurance company premium. Right? I have to pay them whether I get hit or not. It's insurance. I pay them anyway, either way. So that's my utility. So my utility function, my expected utility with insurance, is the sum of these two. Okay? So in other words, and I want to set that equal to 199. I want to say, what X am I willing to pay that would leave me at the same utilities if I was uninsured, as per the answer here. Okay? Well, it turns out if you do that you solve this, you get that X equals 399. You solve this, you get that X equals 399. That is, you would pay $399 for insurance that has a value of only $300. You'd pay $399 for insurance even though the actuarially fair price is $300. You would pay the insurance company $99 more than they expect to pay out to you. Why? Because you're risk averse. Because you're made so much sadder by being left with $10,000 than you are by having to pay $300. If it doesn't work out, you pay $300. Who cares? That's tiny compared to your income. But if it does work out, you're saved from having to starve. So you pay $400. I'm sorry, I pay $399. Okay? You're like, look, yeah, I'll be bummed if I have to pay $400. That's a percent of my income, basically. That'd be a shame to pay a percent of my income for something that doesn't happen. But boy, would I be happy in that 1 in 100 chance where I get hit by a car when I'm not out $30,000. So you will pay $399 for insurance that's only worth $300. That extra $99 we call a risk premium. We call that a risk premium. The extra $99 we call a risk premium. That is the amount that you are willing to pay above and beyond the fair price because you're risk averse. Okay? And what you should go home and show yourself, okay, using the same kind of mathematics, is that, for example, the risk premium will rise the bigger is the loss. Okay, hopefully you can see the intuition of that. The bigger is the loss for a given level of income, the bigger is the risk premium. Likewise, for a given loss, the risk premium falls with income. So the bigger is the loss relative to income, the more of a risk premium you're willing to pay. Okay? You should also obviously see that the more risk averse you are, the bigger premium you're willing to pay. A risk neutral person would not pay a risk premium. Okay? Only a risk averse person will. So the more risk averse you are, the bigger risk premium you'll pay. And the bigger the loss is relative to your income. The same principles we talked about before. So just as so the $43.75 we were willing to pay to avoid that gamble I was going to force on you, that was the risk premium. You were willing to pay $44 to avoid that gamble. Here you're willing to pay $99 to avoid the risk of ending up in that bad state where you get hit by the car. Okay? And that's why people buy insurance, and that's why insurance companies make ungodly amounts of money. In the US, we have a health insurance industry, for example, that earns about $800 billion a year. Okay? Why do they make all that money? Because people are risk averse, and they're willing to pay to have someone else bear the risk of their injury or illness. Okay? Any questions about that? Now, I don't mean by that to say insurance is a bad thing and we shouldn't do it. Risk aversion is the nature of our utility functions. We should be willing to pay a risk premium. It's just you need to understand why, in fact, it makes sense to have insurance in that case. Second application, the lottery. Okay? The lottery is a total ripoff. Okay, I hope you knew this already. The expected value of a $1 lottery ticket is roughly 50 cents. So for every dollar you spend in the lottery, in expectation you'll get about 50 cents back. Okay, this is an incredibly bad bet. Incredibly unfair. An incredibly unfair bet. Okay, on average you lose 50 cents for every dollar you bet. Okay, and that's why and so basically, despite that, lotteries are wildly popular. They've become a huge source of revenue for state governments. A lot of the money the state government's now taken is through state lotteries. Okay, what accounts for the fact that lotteries are so popular? Well, there's 4 different theories for why lotteries are so popular. The first is that people are risk-loving, that we have it all wrong, that actually people like taking risk and the lottery feeds that. Okay? This, of course, we can immediately rule out how. How do we know this is wrong? That the answer is people play the lottery because they're risk-loving. How do we know people aren't risk-loving?
The same people don't take other gambles.
And they spend $800 billion a year on health insurance. Okay? Basically, as a society, we spend in total about $1.5 trillion a year on insuring various risks that face us. We're not risk-loving. Okay? So that's clearly not the answer. Okay? However, there's an alternative, which is that people could be they could basically alternate between risk-loving and risk aversion. Okay? So this is a theory due to Milton Friedman, the famous economist from Chicago, and a co-author named Savage, the Friedman and Savage preferences, where the notion is that basically people are risk-loving, risk-averse over small gambles, but risk-loving over large gambles. So see that go to the last figure in the graph. This is sort of a complicated case. Okay? Basically, the notion is if you take someone, they have a utility function which is initially risk-averse and then becomes risk-loving. That is, in the segment between W1 and W3, okay, that looks like a risk-averse utility function. But once you get above W3, it looks like a risk-loving utility function. So the notion is that basically, for things which can basically make me very poor, I'm risk-averse. I want to insure against events which will leave me on that bottom, which will leave me in that bottom segment. But once I'm going to be above W3, then great, I'm happy to take risks. Then I become risk-loving. Okay? Now, this is kind of a not crazy idea. So basically, the idea, graphically, what I'm showing you here is that B star is utility without the gamble, and B is with. So you see, you're happy without the gamble when your income's low. Once your income's a lot higher, you're happier with the gamble at D than you are without the gamble at D star. Okay? Now that's not a crazy theory, right? The notion is that kind of once I'm rich enough, I become risk-loving. But when I'm poor, I don't want to take the risks. The problem is that this is inconsistent with lottery behavior in the following sense. Most people who play the lottery don't play the Mega Millions. They play tiny scratch lotteries where you bet $1 to win $10. Okay? Or you bet, and people spend huge amounts of money on lotteries with very, very low payoffs. That is inconsistent with this. Because this would say you'd only play lotteries that have big payoffs. Lotteries that have small payoffs, once again, there's no reason to play that and still buy insurance. So if you're buying insurance against being low income, why are you playing these small lotteries that are a ripoff? Because those small ones are a ripoff too. So the existence of the fact that the most popular lotteries are actually the small lotteries is inconsistent with this explanation. Yeah?
So I'm confused. Is it the risk-loving on large gambles?
Yeah, risk-loving on large gambles.
High,
It's basically large. It's basically gambles. It's not the size of the gamble. You're risk-loving on gambles which leave you in a high wealth state.
okay.
So basically the point is that basically if I'm gambling over winning Mega Millions, yeah, I'm a little risk averse, but the truth is, like, Winning Mega Millions would make me so happy I've moved into the risk-loving part of my utility function. But this would not explain why I'd ever play something that pays off $100. Yeah, it's a fancy way of just the intuition you probably have is, gee, I think differently about something which would completely change my life and make me a multi-billionaire. That's something that would make me raise me than the bet I offered you guys before. People are systematically taking terrible bets of the kind I offered you guys before. And that's inconsistent with these preferences. Okay? Third explanation is entertainment, which is that the utility function has in it the thrill of the risk. We only write down utility functions that are a function of consumption, how many pizza and movies you see. But that people have utility over lots of things. One thing they have utility of is the thrill of being able to scratch the thing off and seeing if they won or not. That would actually be consistent with the fact that people pay a lot of small lotteries. If it's the thrill of winning that matters, if it's the scratch-off thrill that matters, then the optimal thing to do, in fact, would be to not play one Mega Million, play lots of little lotteries. Okay? And that would be consistent with that behavior. So one story that is consistent with what we see is that people actually view this as entertainment. On the other hand, once again, it's really expensive entertainment because you're throwing away 50 cents of every dollar. Okay? So you got to get a lot of enjoyment out of that scratch-off relative to, say, going to see a movie. Okay? So that's another theory. Okay? Actually, there's 5 theories. A fourth theory is sort of another version. I'm going to put this in here. It sort of inserts in here. We talked about the fact people can't be risk-loving because they buy insurance. And this alternating thing doesn't work because they play small lotteries. But another theory that might fit here is a theory we call loss aversion, which is sort of a different version of the Freeman-Savage preferences. It's that people are, in general, risk-averse. Okay? But in fact, they're really risk-averse on the downside, and they don't care so much on the upside. So in other words, the point is that when I initially offered you that bet of win us 125, lose 100, part of your reaction was about the risk aversion, but a lot of you were thinking, gee, I'd be really bummed if I lost $100. Not just out of despair, just like, God, I would kick myself. It was one flip of the coin. How could I possibly have been so stupid? Whereas if you won, you'd be happy, but then you go on to the next class. Okay? The notion is that basically it's an extreme version of risk aversion. That basically not only risk averse, it goes further than that. Relative to the starting point, anything which is a loss really pisses you off. So in fact, even that little gamble I offered you, win $1.25, lose $1, you still might not take. Some of you still wouldn't take, right? And the reason you wouldn't take it can't be risk aversion, because it's just too small for risk aversion to plausibly work. It's that you'd just be bummed that you did that, you took that chance. You'd be made sadder by the loss than you made happier by the win. Okay? In that case, that could explain why people spend a lot of money to buy insurance, because they'll be so bummed if things go badly. But they might play the lottery because, in fact, they're sort of around that point, they sort of don't view the money they're spending as a loss. They sort of think of it differently. They think of the loss being that, gee, my house burned down. That's a loss. That makes me really sad. But the dollar I pay to pay the lottery, that's not really a loss. And you know, so I'm sort of risk neutral going up and really risk averse going down. So I'm willing to take gambles that push me up. It's sort of like Friedman-Savage. I'm willing to take gambles that push me up, not gambles that pull me down. But once again, that doesn't really explain the small ones. That doesn't really explain the small ones. That's more the entertainment theory. Then finally, the last theory we have is that people are stupid. Okay? The lottery is, after all, officially known. Its official motto is a tax on the stupid. Okay, and that's what it is. It's a tax on the stupid. Basically, our schools, many of your public schools are financed by taxes paid by stupid people. It's sort of ironic. Okay? But people just don't know. I mean, how many of you, I mean, you probably all had a vague sense that the lottery wasn't a sensible thing to play. But how many people actually knew it was that bad a deal, as I said, that you actually was a 50% expected payoff? Okay, a few of you knew. But most of you knew while it was a vague sense of a bad deal. You didn't know how bad a deal it was. This is sort of hard to figure out. Meanwhile, you see on TV the guys win these bazillion dollars and you get the thrill of scratching it off. Okay? So basically, if people are just stupid, then that could explain it. The problem is it matters a lot for government policy which of these is right. Because if A through C is right, if 1 through 3 are right, then the government should go ahead and allow lotteries, and there's no reason why the state shouldn't run a lottery. In fact, let's take the entertainment theory. If this is really entertainment, and the state can make money off my entertainment, then that's a win-win, right? I'm happy because I'm playing the lottery. The state's happy because it's financing schools. That's a win-win. So if these are right, you're going to want to encourage state lotteries. But if this one's right, we don't want to have them. Because basically, essentially, that's a terrible way to raise government revenues, is to tax stupid people. Okay? There are much better ways to raise government revenues. We'll talk about taxation in a couple of lectures. But clearly, taxing the stupid is not going to be an optimal tax. Yeah?
I can maybe sort of understand why people would prefer smaller lotteries over bigger lotteries, because they think in their mind that smaller lotteries, they have a much bigger chance of winning than the bigger lotteries. So in that sense, their expected payoff in terms of like utility or what they're just expecting is a lot higher for the small ones than the bigger ones, even though the bigger ones might end up making them a lot happier than just winning.
But that's sort of an entertainment theory, which is my utility derives from the win. You have a theory in mind where my utility derives from the win. Because if it's about dollars, that wouldn't explain it. Because I win so many more from the big one that it would compensate from the frequency with which I win the little one. But if I actually, in my utility function, have the joy of seeing that winning thing, then that would explain it. That's an entertainment theory. You're saying in my utility function, I actually get joy from scratching off a sequence of winner, and so much joy that I'd much rather take a 10% chance at a small win than a 1% chance at a huge win. Because then at least with the first one, 1 in 10 times, I get that joy of the scratch off and seeing it's a win. So that's sort of an explanation. And that would say that lotteries are good, and if the states can make money off them, the other way economists might think about lotteries, they're voluntary taxes, right? The public doesn't like taxes, okay? Here's a voluntary tax. You never hear politicians getting up and railing against the horrible evils of the lottery, okay? Sometimes groups do, sometimes, outside groups do and stuff, but politicians don't. But those same politicians will go on and on about how terrible taxes are. I'm going to cut your taxes. Taxes are terrible. Okay? Well, the lottery is a voluntary tax in that sense. And I might say, look, there's no reason to oppose it. It's a voluntary tax. It's those involuntary taxes that cause problems in society. Well, whether we want to buy that story or not depends on how much we think it's being played because people are stupid or not. Okay, let me stop there. So that's a great example of how a little bit of extension of our model can really enrich our understanding about a lot of decisions that we make in the real world. We'll come back and talk about another version like that later, and that is the case of thinking about savings decisions and thinking about individual decisions on how much to save and how much to spend.